Cool, you're far away. All right, good morning everyone. Hope everyone's well. I haven't started marking the assignments yet. I've got one last lecture I have to give in this mixed reality course that I haven't finished putting together. So that's on Thursday. Let me finish putting that together and then I'll mark the assignments and get them back to you guys next week. And also I will try and make sure you get the next assignment on Thursday so you can start on that. Okay, so we're just going to continue on talking about graphics, so just a quick refresher so I can make sure I know where we're up to. So we started last week, we looked at a little bit of Unity and then we started talking about graphics. We talked about primitives and then I said don't worry too much about them because you're probably never going to have to work at a level that low, but it's nice to know sort of what's going on behind the scenes, particularly when we come back to things like surface normals later on, so you hopefully we'll understand what's going on there, and when things go wrong, you'll know how to fix them. And then we got into transformations. We talked about things like translation, scaling, and rotation. We looked at some examples of that, and we talked about sort of what they mean, what the maths behind them is. I even went to the trouble of going through some matrix multiplication just to see if I could still remember how to do it. And then I think we finished up with rotation around a pivot point from memory. And we were looking as well at some examples in Unity in addition to the stuff in processing. So we had the example if we had that bat effectively, where's he going? We have a bat and then we put the killer whale as a child of it. Where's the killer whale? And we make them roughly the same size so I can see both of them. Oops. What is going on here? Right, so we have a bat and a killer whale, and effectively we're talking about rotating the bat with the killer whale as a child. And we talked about how if we wanted to rotate the killer whale around some pivot point, so let's actually put the killer whale to the side that way, so we can see our bat there. So if we rotate around our bat, we'll rotate the entire whale around that point. But if we wanted to say rotate the whale around his tail and keep him where he is, we'd have to move the tail of the whale to that pivot point, do the rotation, and then move the whale. That's my point. Move the whale back where it came from. And so we talked about that a more direct example in processing with this here. So if we wanted to rotate this triangle, if we rotate around that pivot point, it would rotate the triangle, keeping that distance from the pivot point the same. But if we wanted to rotate around that corner, what we'd have to do is shift that so that corner was at the origin or at the rotation point. So we do that by, if the point is at x, y, z, translating by negative x, negative y, negative z, doing a rotation and then translating back. Everyone remember that? Yeah, more or less. Probably still a bit grey, but that's okay. So there's just a couple more things. So the order of our transformations is very important, and we've sort of, this is really a follow-on from this sort of thing. So if we were to do I'm going to move, I'm assuming this is your guys' artwork, is it? Take these down. We can pin them to the fridge in the break room if you guys would like. So if we use this example again of this triangle, well actually we'll do the example which we've got on the slides here. So we have this arrow here which is sitting at the origin, and we're basically doing the same operations. We're rotating by say 30, 20, 30 degrees, we'll say 30 degrees counterclockwise. So we're taking the arrow and we're rotating it 30 degrees counterclockwise, and then we're doing a translation by maybe let's say 3 units in the x dimension. And this has the exact same operation, so we're translating it by 3 in the x direction, and then we're doing a rotation about 30 degrees counterclockwise. But the difference is if we do the rotation first, because this is sitting on the origin, the rotation will happen around that point, and then the translation will be from that point. Ooh, try not to break the TV. Whereas if we do the translation first, what we're doing is we're moving it out, and then when we rotate, if you remember, we have this concept of the world coordinate system, or I sort of said imagine a 3D cursor like a mouse pointer where all the actions happen from. If we move it first, when we rotate around that cursor, we're actually going to rotate the object as if it was sitting on an arm, like so there was an arm sitting out here and we're twisting the arm round and that's turning as well. So it's very important to remember these order of transformations because doing the same operation or the same sequence of operations in a different order can yield a very different result. So in this case, you know, the triangle's still being shifted, it's still being rotated, but because this one was rotated around a point that it's further away from, it's actually come up off that x coordinate line. So here you can imagine this would be x is 3, y is 0, and here x is probably slightly less than 3 and y is more than 0, because what has effectively happened is we've done, rather than doing that, rotation of 30 degrees around here, we've instead done a rotation of 30 degrees here, and our previous arrow has now moved up that way. So that, if this is a distance 3, this will still be a distance 3, but we can use our Sokotoa rules that we talked about last week to figure out the position it would be now. So the x value for this one is probably slightly less than the x value for that one, because that would have rotated in a curve, and the y value is obviously higher. Does that all make sense? I know I'm not probably doing the greatest job explaining this concept, but I always struggle to sort of explain why the order of rotations is, is different between the two things. But really it all comes down to all operations happen relative to this point here. So the origin of the world, all operations happen relative to that. So if we move an object away from it and then do a rotation, we're effectively rotating it around that point. Whereas if we do the rotation at that point, we're actually just twisting it on that point. It's one of these things I'd recommend. The more you play with Unity, I think the more this will become obvious to you as well. So basically, when we're talking about doing multiple transformations at once, we're talking about doing composite transformations. And basically, it's really one of these things that is probably easiest to play with, but the idea is if we have a set of points x, y, z, or a point or set of points x, y, z, we're going to multiply each of these operations in order. And depending on what transformations they are, this may or may not be different. So for example, if we have if we are starting from a point 0 and we move, operation 1 is move right 3, so right 3, and then operation 2 is move up 1. That will actually give us the same result as if we do these operations the other way. So instead we move up 1 and then we move out 3. So reverse those operations. So in certain cases, the order of operations, depending on what the operations are, won't end up in a different result. Certainly anytime you're talking about something involving a rotation though, it likely will, because if this was a rotation, we're going to end up yeah, I've already explained. I'm not going to go, I don't think I can do a better job explaining it than that. But basically, anytime we're talking about a rotation, certainly it will, well, I guess it's probably almost more if we're talking about mixing and matching different operations, so a translation and a rotation. So if we did the translation first, and then the rotation will be different if we do the rotation and then translation. If we do 2 rotations and 2 translations, or 2 rotations, it may not necessarily matter depending on how far we're rotating. If we do 2 translations, it probably won't matter. Likewise, 2 scaling, but mixing and matching any of them will almost guarantee that the order will matter, and that includes things like scaling. If I did a scaling operation, so I have my box here, and then I scale it down to half its normal size and shift it out here. And then if you remember that example we saw with the 2 boxes the other day, if we did the move first, and so that's now the big box, and then we did the scale, that would actually effectively appear like it's moved back a little bit, because as we scale all those x values for each of those points, it decreases slightly. And just as a reminder, we had this example here. Let me reset position, reset rotation. So just as a quick reminder, if I take this bat and use the scaling on the bat, so as it approaches 0, you'll see if we look at the distance between the front of this bat and the front of the whale, the distance, if we just look at those grid lines, it's about 1.5 grids away. Now it's about 1 grid away until it eventually gets to 0. So doing a translation then a scale will appear to move it, whereas if I scaled that whale first and then translated it out, it would have a different end result. So when we're talking about doing multiple transformations in Unity, probably the easiest way to think about it is actually doing a separate game object for each transformation, and then changing the hierarchy of that. So let me see if I can do a little example here. So I'm going to do two different things. We're going to do translation, and we're going to do a rotation, and then I'm going to stick, let me think if I've got anything, what I can stick on there. Where is that? Other way. There we go. Okay. So just actually I can probably do one better. Error. So I'm going to do some stuff we haven't really talked about yet, but we will look at it soon. Do. Save image as. Okay, so don't worry too much about what I'm doing now, because we will look at this. I've just lost my download menu. I will talk about what I'm doing here in a few, well, probably either at the end of this lecture or in a, maybe on Thursday. Okay, so there's my error, create material. There we go. Okay, that was a very long-winded way to get an arrow on the screen, but we're there now. So, where's PowerPoint? So, okay. So we've talked about here the orders of translations. We have a rotation and then a translation and translation rotation. So if we were talking about doing this in processing, we'd write GL rotate or then GL translate. Actually, I should probably open processing. Translate and then a rotate, or a rotate and then a translate. Because Unity uses this concept of a scene graph, instead what I've done is I've put these translations and rotations as separate game objects. Each one is sitting on top of the other. So we have a translation first, then a rotation, then a quad. So let's have a look. So I used the examples before. We have a, let's do it the other way around, sorry, first. So we have a rotation followed by a translation. So if I do a rotate first, and let's rotate around X. Let's rotate around 30 degrees in the X-axis, and then I'm going to do a translation of, what's going on here? Oh, that's moving in the wrong direction. Not that one. 3. Okay, so this one has done a rotation, then a translation, and then a quad. And it's actually given us, because of the way the scene graph is set up, it's actually given us closer to this bottom result. So we've done the rotation, and effectively in this one what it's saying has happened is we move out and then we rotate around this point here. But in Unity what's actually happened is because it's rotated the arrow first, so our first operation went from this arrow with its X direction, or in this case it was a Z direction, facing this way, and then we've rotated it by 30 degrees. What that's done is it's pointed at its Z direction 30 degrees from the original Z direction, so when we move it 3 units, this one would go in a straight line to here. And this one instead has come on a straight line to there. So that's what's happened in Unity. It's kind of the reverse of the order that is shown in the slides. So there's been this rotation at first, which has rotated everything by 30 degrees. Actually, turn that one off there. There we go. So we can see in the axes that's been rotated 30 degrees. Then we have this translation, which has shifted it along that x-axis, or the z-axis, I think in this case. So it's shifted it along that z-axis, so we can see it's moving along that blue line, and then we have our quad there. So if we do the same thing again, but this time we put using the exact same rotation and translation values, but change the order of them. So we're going to have a value of 3 there, and a value of, oops, what's going on here? There we go. I was going to say something's gone wrong here. So we have a translation of 3, and a translation of 3. We have a rotation of -30 and a rotation of -30, and then we have our 2 quads. And we can effectively see these 2 cases here. So this one here maps up with this one, and this one here maps up with that one there. So in this case, we've started from the origin, which is, I don't actually have an origin point, but it's over there. Let me put one more in there so we can say origin and make those 2 children. So we have our origin. For our one which is up, we do the rotation first, then we move 3 units along that z-axis to get there, and then we have our triangle. For the other one, we have our origin which is there, we move 3 units across, then we rotate, and then we draw our arrow. So it's the 2 exact same operations, but in a different order have given us 2 very different results. And it's just something to be wary of when you're doing any sort of 3D graphic stuff, that you have to be very clear about the order that you do these operations, otherwise you will get the wrong result. And fortunately, in things like Unity, it's very easy to correct if you do these things, because you can see what's going wrong. It's obviously a little bit different in code because you have to run it and then test it. And especially in code, it's even worse in that if you do the wrong operation, you can end up with all your content out of view of the camera, and then it's really hard to figure out, I'm rendering something, but it's actually behind the camera because I did my rotation and then my translation rather than my translation and my rotation. So be grateful we have Unity because it makes life so much easier in that respect. I'm actually working on something with my company now which is not in Unity. We're translating some of our other stuff into native Android code, and so I've had to go back to writing everything in OpenGL. And I spent most of yesterday working on it to get all the stuff going, and then ran it, and I saw nothing. And then I changed some things, I moved some stuff around, I ran it, and I still saw nothing. And then I decided that was enough work for the day and to go home. So as far as I'm aware, it is being rendered. I just have no idea where it's being rendered because I don't know what the camera's pointing at. So yeah, be grateful that we have things like Unity now, and your assignment will be in Unity, so it should be a lot more manageable in that if something isn't appearing where you think it is, at least you can go to the scene view and have a look around and say, oh, okay, that's because my camera is looking that way, and that's looking at the side of my two arrows rather than the front of it, so I'm not going to see anything. So I can just move my camera around, whoops, and rotate it, and lo and behold, there are my two arrows. Okay. Anyway, that was a lot of messing around to illustrate what is probably quite a simple point. You guys probably immediately understood, but that's okay. So yeah, just to finish up the stuff about transformations. So in addition to composite transformations, we may be interested in doing independent transformations. So if we want to draw one object, that's fine. You know, we move it out to wherever we want to put it and we draw it. But if we want to draw two objects, we have the problem that because everything is done on this world coordinate system, if I start, here's my origin here, and I move this out here and up here and then rotate it in some way, and then I want to draw another one, I have to figure out, instead of where the relationship of this is to the origin, where the relationship is for this to the origin, I have to figure out where the relationship of these two objects are to make sure that when I've moved the cursor here and drawn this, I now know how to get the cursor over here and draw that one, which is doubly hard if this one's moving. So we've seen examples where we have an object which is moving, and every object which is drawn after it will move accordingly. So if you remember from last week, we had the example of the two boxes, and they were moving across the screen, and one appeared to be going twice as fast as the other one. We were actually only moving them at the same speed, but because this one was moving based on this one would move 1 unit and drag that one along, and then that would move 1 unit. This one would move 1 unit and drag this one along, and then that would move 1 unit. And so every time it was effectively doubling the speed. So we may want to apply different sets of transformations to different objects, but transformations accumulate. So if I do a move and a rotate, I have to then undo that move and the rotate to get back where I was, so I can make sure that I draw my objects in the right place. So there are a few ways of doing it. We can undo a transformation by multiplying its inverse. If I'm starting at my origin here, and I move this over to here, and I want to draw this relevant to the origin, I can move back the opposite of that and then move it out where I want it. Or I can reset the matrix to identity. And what resetting the matrix to identity means is basically our identity matrix. So if you remember back, we looked at those 4x4 matrices the other day, and we looked at how if you do a translation, it changes this value, and if you do a scale, it changes those values, and if you do a rotation, it changes blocks of 4 values. The identity matrix is one which looks like that. So the identity matrix is all zeros apart from the diagonals, which is 1, and if we just have a quick look at that as to why, if we remember from our matrix multiplication from last week, we multiply a row across by one of those. So, and then we add them all together. So we're going to go 1 times x. I'll put over this side. So our resulting values will be 1 times x plus 0 times y plus 0 times z plus 0 times 1. So that will be x. 0 times x, 1 times y, 0 times z, 0 times 1. Should be y. 0x, 0y, 1z, 0, 1. And 0, 0, 0, 1. So we multiply any point by the identity matrix will give us the original point again. So the identity matrix is effectively the origin. When we first start our, so I talked about how effectively as we go around, do transformations and stuff, this matrix continues accumulating. So if we do a translate, this will change. If we do a scale, these will change. If we do a rotate, some numbers in the middle will change, and those accumulations will continue changing. And when I talk about the cursor or the world view or model view coordinate system, I'm effectively talking about what is being stored in here at the moment. So this will continue to change as we do all our operations. If we set the model view or the cursor or the world view or whatever you want to call it back to the identity, it'll put it back at the origin where everything started from the beginning. So again, we start from our origin, we move out, we do some stuff, and then if I say set the model view back to identity, it will put me right back where I started, and then I can go off and do other things. And then the last one, and this is usually the most common one when we're talking about programming graphics, is this concept of a stack. So does everyone know what the concept of a stack is when it comes to computer science and programming? No? Okay, cool. So a stack is a data structure in computer science which basically works in the same way that it's you would expect it to do. So it's usually, or it's often represented as like a column, and what we can do is we can push stuff onto the stack and we can pop stuff off of the stack. So if I say push the letter A onto the stack, we will put A on there. And then I can say push the letter B onto the stack, and we'll put B on there, C, D, E, push them all on one at a time. And then what I can do, so this is the things that I've pushed. And then what I can do is I can pop. And what popping will do is it will take the, or return thing which is on the top of the stack. So if this is our stack at the moment, I say pop, what's going to happen is I'm going to get the first value E, and then I'm going to remove that from the top of the stack. And then if I do it again, I'll get D, and remove that from the top, then I'll get C, B, and finally I will get A, and the stack will be empty. So you can see looking at this, what a stack does is effectively it reverses the order that we put things in. So why is that useful? Just going to come back to that. We'll do this one. So imagine we have this set of operations here. So we start with our identity. I'm just going to put I for identity. And that's kind of always at the bottom of our stack, regardless of what we do. So then we're going to do this translate. So we're going to move our coordinate system or our model view matrix by tx, ty, and tz, and then we're going to rotate it by some amount. So we're shifting, and then we're doing a rotating. So that will set our current transformation or our model view matrix to currently be a translation and a rotation. And then what we do is we call push matrix. So our current transformation is equal to translation plus rotation, and we're going to call push on that. So what we're going to do is we're going to save this translation and this rotation, because push matrix is literally just a graphics thing that we have a stack and we just push the current transform. So whatever the current transform, the current model view, the current cursor, whatever you want to call it, we're going to push that into the stack. So then what we can do is we can go and do a scale. So we're going to scale some things. So we've done a transform, we've done a rotate, and we've done a scale. And then we draw this cube. So we end up with a cube which has been translated, rotated, and scaled. And then when we call pop matrix, what we're going to do is we're going to get whatever's on the top of the matrix, the top of the stack, and we're going to set the current matrix to be that. So we're back to the translation and rotation. Okay, so this is a really terrible example because it's not very clear at all. So let's try and do a better example. Let me get a red pen. Okay. So we have our stack. We're at the identity. So at time 0, we're sitting at the identity. So let's do a translation. We're going to translate out 3 units in the x dimension and up 1 unit in the y dimension. And we're going to call that position 1. So our current transform is a transform 3 in the x by 1 in the y. So we can push that to our matrix. And if we wanted to, we could, draw some shape there. So we've drawn a little box there. Okay, so then let's go and do something else. We want something which is a child of this. So let's do another translation. This time we're going to do a translation of 1 in the x, and then we're going to rotate 30 degrees in the y, and then we're going to move it in this direction, so this is the y direction again by 2. So now our current transformation, God, I'm making this really hard for myself, is a translation plus another translation plus a rotation plus another translation. And then we draw another shape. So we've got a square now, and we've got a circle which is related to the position of that square because we've just kept going off that square. If that square moves, this circle will also move along with it because it's related to it. Okay, so what if we now wanted to draw a triangle which was related to this position of the square, but it wasn't related to the position of the circle? So if I kept on going from here, if the circle moved, that triangle would also move, but I only want it to work from the square. So what I need to do is I need to get back to position 1 again. So what I can do is I can call pop matrix, which will take, so this is our current transformation, it will take the transformation which is in there, C3, 1, C equals transform 3, 1, and effectively will undo all of these green operations and put us back here. And then I could go off and do some other transforms and put a triangle in there. So there is an example coming up, this one here, which puts it into perhaps slightly more real world terms. So imagine we're trying to draw this house up in the corner here. And this one, again, is probably slightly more complicated than it needs to be because we basically draw the house and then we draw some trees and so on and so forth. But let's have, and in the house drawing method, we call a function called house. But let's jump over to house and see what's happening. So in our house drawing method, we call push matrix to save the current position. Then we do a translate out by 2 units and we draw this door. And then we call pop matrix. And then we call push matrix and we move by 4 units and 3 units and we draw this window and we call pop matrix. So if we didn't, because we have this push matrix and this pop matrix, effectively what we're doing is we're saving the position before we draw the door, and then we're loading the previous position. So that means that anything we draw after the door isn't actually attached as part of the door. Because what I don't want to do is if I'm drawing my house just looks like an arrow. If I draw the door here and then I say, okay, and then from drawing the door, let's move up here and draw the window. If I then decide, actually, I want to put let's put the window up here. If I have my door here and then I draw that and then I move up here without a push and pop matrix and draw the window, if I then say, actually, I'm going to move my door to the other side of the house, move it over here, because we haven't called push and pop, the window will follow it. And so the window is now drawn off to the side of the house. So what we want to do is for objects that shouldn't be related to each other, we should always call push and pop before and after we draw them to separate them out logistically. So I would draw my door, and then I would call push matrix, draw my door, and then pop matrix, and then I would move and draw my window, and call push matrix, draw my window, pop matrix. So that way, if I want to move my door over here, the window is actually separate from the door logistically. Like after I've drawn my door, I say return back to where we were before I did any of that moving. So it's a little bit, again, one of these things which is a little bit challenging to try and explain. There are some processing demos that hopefully may make things slightly clearer. Oh, that's really useful. I didn't actually. Okay. Basics, transform. So on this one here, this is quite a neat little example that shows a little arm. So as I move the mouse left to right, it rotates one joint of the arms, the shoulder, and as I move it up and down, it rotates the other one so I can make it say hello. And if we look at this, this is actually a super simple example. Just ignoring all the setup stuff. We effectively have two segments, which is a line. So we move out by a certain amount, we rotate by a certain amount, and then we draw a line by a certain amount. So what's happening here is we draw segment 1, which is this shoulder, and it starts at x by y, or x by y, and then we rotate by some amount of angle, and then we draw, and it is sig length, so segment length long. So we move out here, down here, rotate around, and then draw that line. And then for the second one, we call move it out by seg length by 0 and draw a line at angle 2. So because our cursor is already sitting here pointing in this direction, we draw the line and then we move the cursor down to here, and then we draw the next line, so it's always going to appear at that joint. So because of these cumulative things, all we have to do is draw this line here, and then say move to the end of that line and draw again. But if we have a push matrix here, if we put that pop matrix, if we put a push and pop matrix rather around each segment and ran this example again, you'd see now those two arms are independent. So this arm here is still x units across by y units down and rotated around and then drawn. But this one up here is now, because we call push matrix before we draw this and pop matrix after, we actually go back to the start. So now when we move by seg length, we're actually moving seg length from the origin. So we're moving out the length of that from the origin and then drawing that second line there. So yeah, does that make sense? Hopefully, kind of. It is.
Except how do you define the point that is started here?
The point, which what, sorry?
No, so here the two lines are independent, but before when they were connected, the bottom point in the top line was the one that was moving.
Yep. So in this case here.
Yeah. So.
Okay. Yeah. No, that's all right. I will do my best to explain it. It does get easy. This is pretty much as complicated as it gets. So I always struggle to explain this because it takes quite a special way of thinking. Okay. Here is our window. So we start for our identity matrix. We're starting at this point in the top left corner, and we're saying x is this direction and y is that direction. So that's where we start. So what we do, if we shoot back to our code, is we have these values x and y, which is width divided by 3 and height divided by 5. I can't be bothered figuring out what they are, but let's say x is 1 and y is 1. So, and this is some amount. So what we do is, in our code, our segment code, all it does is it moves to the position of x by y, it rotates by a, and then it draws a line which is seg length long. So we move out an amount in x and an amount in y to get to here. So that's the first step. Then we rotate by angle A, which is this first angle. So we're going to rotate this around. So let's say now our new position goes such that x is pointing that direction and y is pointing that direction. Yep. And what we're going to do is we're going to draw a line. It'd be easier if I just brought my mouse over here. We're going to draw a line sig length long, so that's x position, y position, x length, y length. So we're drawing it sig length long in the x-axis. So what's going to happen is we're going to draw our line in the x-axis of a certain length. And so we're going to then draw our next line. So we're not undoing the movement or anything. We've done the push matrix and the pop matrix around both segments. So our next thing is we're going to move by sig length in the x direction and 0 in the y direction. So keeping in mind that the x direction now points down this way, we're going to move down sig length in the x direction and y and the 0 in the y direction. And then we're going to rotate around some amount such that y now points that direction and x points that direction. And then we're going to draw our second line. And so if this is angle 1 and this is angle 2, you can see the only two things which actually change is angle y and angle 1 and angle 2. So this first angle will rotate everything around that first point. So this line and that line will effectively get rotated by that. Angle 2 will only affect that second joint there. So as we go back out, if I try and recreate the shape I've made there roughly, it's kind of like that. So we have our first line, we've moved x by y, we've rotated it round so that the x direction is now this way and the y direction is that way. We've drawn our line and then we've moved to the end of that line and we've done another rotation that way and then we draw the second line. So this one, doing that first rotation will move everything like that. Doing that second rotation just rotates that second part. Does that kind of make sense to everyone, hopefully? Fortunately, the good thing is, again, Unity just covers over all of this nicely with a scene graph. So we can definitely recreate that experience we just had. So let's do that quickly. Let's grab a couple of cylinders. So I've got 2 cylinders here, and let's make them a little bit longer. So say I want to recreate that experience. Well, okay, so let's, just to make it easier for ourselves again, let's create a new object called origin. And so that's going to be the origin of everything. And let's put cylinder 1, move that around. So let's put cylinder 1 at, yeah, I don't know why it always does, puts them in weird places. Okay, so there's my origin. Let's put the end of cylinder 1 at the origin. So I'm going to move that down to about there. So let's just hide that second one. So cylinder 1 is now basically at the end of that origin. So if I make that a child cylinder of the origin and rotate that, you'll see that's effectively our first joint. And then what I can do is I can move cylinder, let's call it cylinder 2. Let's move that down so it is now at the bottom of that second joint. And if we make that a child, just trying to think, maybe I'll make a separate object called joint and we can rotate that instead. What's going on there? Sorry, bear with me for a second. It says origin cylinder joint needs to be at the bottom of that. And there we go. Okay, cool. So we have our origin, or let's call it joint 1, which is at the top. And then the first cylinder sits just as a child of joint 1, and then we have joint 2, which is at the bottom of the bottom of the first cylinder and the top of the second cylinder, and then we have the second cylinder under that. So with joint 1, if I rotate that, everything will rotate. If I rotate joint 2, ooh, what's going on there? That's really weird. Okay, I'm not quite sure what's going on there. That should have rotated around. Ah, I know what it'll be. Because there are scales occurring in there. There we go. So the rotation, because I'd scaled the cylinders, the rotation was also being scaled as well. So we have 2 joints, one, now everything's out of whack. Sorry, bear with me for a second. Okay, cylinder 1, okay. So rotating around joint 1, we'll rotate everything. Rotating around joint 2, we'll just rotate that second joint. But rotating around joint 1, with a rotation around joint 2, we'll rotate the whole thing. So effectively what we've got in the processing script here, with the translate and a rotate, well, we have our translate is effectively this, so we've moved the position of the cylinder so that it's sitting on that joint, and the rotate is the rotation around that joint. So everything we can do in code, we can do in Unity without actually having to write any code, and it's probably a lot easier to figure out and to visualize, because we know it's going to rotate around those things, around that point, so we just have to position everything so that as it rotates around that point. Okay, so Unity uses a scene graph rather than a transformation stack, which allows us to represent the entire environment in a tree structure. So normally a scene graph looks more like that. So we have a scene root, and then we have a transform and terrain and everything. But if we took this and rotated it 90 degrees sideways, we basically have this. So we have untitled is the name of my scene, but effectively acts as the root. And then we have each of these is a separate branch in the root. And then each of these, we go down a separate layer. So the idea behind looking at one of these scene graph trees is that at any point, if we do some transform here, it will affect all of its children. So if I shifted this along, it's going to shift this along, it's going to shift all of these along, and so on and so forth. But it only works from top to bottom. So this transform will move all of its children, but if I transform just this tree here, it's actually not going to affect that tree, it's not going to affect any of the siblings or anything. Transforms only affect the things that sit underneath it. So in Unity, we don't actually necessarily have a differentiation between a transform and a different object. Other things, other scene graphs might. There's one which used to be really popular called Open Scene Graph, and that differentiated to an extent between a transform and a terrain. Transform and a visible object. So I've tried to sort of mimic that idea a little bit here, in that we have joint 1 or joint and that should be joint 1 and joint 2 really to make sense. But these two joints, you'll notice they have no components attached to them. They're only a transform. Their only purpose in life is to have their rotation changed. They don't actually draw anything, but when you change the rotation, they affect their children. And then we have these 2 cylinders, and all they are there to do is be drawn. So that's kind of similar to this setup in that we have separate transform, and then we draw a terrain, or better yet, transform, and then we draw a house, and then we transform from the house and we draw a window, and then we transform from the house and draw a door, and then we transform from the door and draw a door handle. So the idea behind this is if I move the house transform, the door and the window will also move relative to the house. But if I move the window, the house will stay where it is and the window will just move. Likewise, if I move the door, the house will stay where it is, the window will stay where it is, but the door handle will move when I move the door. So we're basically using this structure to define sort of like a more like a cognitive way of how things are connected together. So A window is a part of a house. So if the house moves, the window should definitely move with it. You know, I don't want my house to slide along and my window stays where it is. So the window is a child of the house, it will stay attached to it. Likewise, the door is a part of a house and will stay attached to it. But the door and the window, they're both parts of the house, but they're kind of independent. If I move the door, the window doesn't have to move. But the door handle is a part of a door. It's pointless moving the door handle and having the door stay stuck on the wall, no longer attached to the door. So the door handle is a child of the door, so that when the door moves, the door handle moves. But the door handle can move independently of the door. So I could say, actually, I'm going to put the door handle on the other side of the door, and so on and so forth. So scene graphs are a nice way. If we go back to when we talked about object-oriented programming, and we had this concept of let's take a whole bunch of properties which are related to each other and put them in a class, a scene graph sort of takes that idea to graphics. So it's like, okay, well, what's the relationship between all these things? Well, we have our house, and a house has a window, and a house has a door, and a door has a door handle. So we can put them in the scene graph like that so that they all behave as we would expect. When I move the house, the door and the window and the door handle will all move, but moving the door isn't going to move the house. Okay, does that kind of make sense, hopefully? Cool. It is, that's probably about the hardest thing to explain in computer graphics that we're going to cover anyway, is the nature and relationship behind these all these transforms. And you can even see, as somebody who's been doing it for a very long time, you know, initially I had scaled these cylinders, and then when I rotated it, the rotation went all wacky because I'd forgotten that I'd done the scale. So I was scaling and then rotating, which caused the scale to go, or the rotation to bend the cylinder in a really twisted way. So even as somebody who's done this a lot, like, it is still easy to make mistakes, so don't beat yourself up if you do. But it's one of these things that you can quickly, the more experience you get, it's not that you're going to make well, you will make less mistakes, but it's not that you won't make any mistakes, but it's when you make mistakes, you'll be able to figure them out a lot quicker, hopefully. Okay, let's take a break there, and then we'll move into cameras and view volumes. Awesome. That's all right, I can get it, I'm already up. All right, cool. So, we're going to move on to the next topic now. Hopefully you guys are sort of vaguely comfortable with the transformation stuff. As I said, you know, the assignment and everything is going to be in Unity, and Unity sort of encapsulates a lot of the stuff underneath it. So if you're still a bit, you're not so confident with like the coding side of it, that's fine, because a lot of that stuff you can do in Unity, just in the scene editor. We will be looking, when we get back to Unity after finishing the graphics part, we will be looking at doing the coding side of things in Unity as well, including stuff like doing transformations in Unity. But yeah, so that's, hopefully you're okay. If you have any questions or whatever, you know, you can always send me an email or drop by my desk and ask. Otherwise, we're going to move on to cameras and view volumes, because they're quite important as well. So to date, everything that we've talked about has effectively been kind of theoretical geometry. So when we talk about having a 3D model or something in the environment, or even, you know, a primitive, really all we're talking about is a bunch of numbers. So if we have some triangle in space, all we have is really 3 coordinates which represent the 3 corners of that triangle. That's all we're dealing with. When we talk about transforming those this object around, so we do a translate, a rotate, or a scale. All we're effectively doing is taking this, changing this matrix here, and then multiplying each of those points by it. And they're all happening kind of abstractly in the computer, and you know, it doesn't actually mean anything, because none of this, we've actually told it what it should look like when it appears on the screen. So effectively what we're doing is, when everything we've done so far with our primitives and our transformations, is effectively we've described the relationships between various objects. The various objects and their relationships. So we might put a lot of primitives together to make this object, and we might make a lot of primitives together to make this object, and then we might put them in space somewhere relative to each other. But what we actually get, what we experience in the real world is just a slice or just a view within that 3D world. Just in the same way that all of us, what we see at any point in time is just a view into the real world. So within this room, there are tables, there are chairs, there's people, there's laptops, there's all sorts of stuff. So all of those are, you could effectively think of objects made of primitives, and they all have different transformations relative to each other or relative to something. But for us as participants experiencing this world, we all have our own separate views into this world. So what I can see of this world is different from what you guys can see of this world. Each of you has your own perspective and your own view. And so we have the same concept when we're talking about 3D graphics. And we do that using this concept of a virtual camera. So a camera in 3D graphics is the same as like a camera or a video camera in the real world. And effectively, the idea behind it is that it represents a single view within a 3D world. So if we were in this room and I was to draw, paint a picture or take a photograph from my current perspective here, it would be one view into this world of objects with their relationships to each other. And that works out because what we're talking about is effectively a 3D environment, but what we actually see as humans is displayed on a 2D display. So, I don't get a 3D view into the world, even if we're doing like, wearing a head-mounted display, which gives the perception of 3D. That's actually just two 2D views, one for each eye, and because they're rendered at slightly different places, it gives the perception of depth. But it is still actually only a two-dimensional view. So what we basically do is we have this concept of a camera, and a camera is an object, or in more programming terms, it's really a position in space that we are looking into the world from. So our camera has a position, so the camera could be here, or it could be here, or it could be here, or it could be anywhere, and it has an orientation as well. So if it's here, it could be facing this way, it could be facing this way, it could be facing this way. And depending on those two things, it depends on effectively what can be seen of this 3D environment. So the camera also has a view volume, which defines how much it can see. So if I'm looking right now, I have roughly, I can see my hands to about there. So that's, approaching 180 degrees view because of the way the human eye evolved. It allows us to see quite a wide range, and likewise quite high and low. But if something was to happen behind me, it's out of my view volume, I can't see it. Or likewise, if somebody was standing just to the side and behind me, I likewise couldn't see them because that's as far as my view volume is. So the view volume basically defines exactly how wide we can see. Sometimes it's called a frustum as well. It's effectively the same thing. So the view volume depends on a number of things. So it depends on the ratio of the screen. So if we're looking at a screen this, it needs to be, maybe 1.5 times as wide as it is high, and so on and so forth, to make sure that we don't end up with like black rectangles from where we can't see from the side. But we can also change the view volume to give different effects. So if I wanted to make the effect of looking through a telescope, for example, I might want my view volume to be much smaller because I'm actually only looking at a much smaller area of space through the lenses of a telescope. Then finally we have clipping windows, and clipping windows are effectively kind of the top and the bottom of the view frustum. So ideally, in the real world, we don't have clipping windows, so I can see something right up until it touches the lens of my eye. But in 3D graphics, often that's not really a good thing. So for any of you who were gamers back in the 90s, when the first Tomb Raider game came out, it had massive issues with the clipping windows. It was a third-person game, so effectively the camera sat behind your character, and as you turned around, the camera was always looking over her shoulder. Except if your camera, the game had a lot of like jumping puzzles and stuff like that, and if your character was standing with her back to the wall, the camera would be on the other side of the wall, and you couldn't actually see anything at all. So what they often do these days is they will say, well, let's put a clipping plane, particularly in a third-person game, let's put the front clipping plane directly behind our character, so we won't actually, anything between the character and the camera, we just don't render. It's like it's invisible. So these clipping planes effectively, like the view frustum, say, let's only worry about 3D objects which appear inside the two clipping planes. So if it's too close to the camera, we don't want it to block the camera. You know, the Lara Croft is standing in front of a wall and all we can see is the wall because the wall is between her and the camera. Let's just say, okay, well, anything which is closer to the camera than the character, let's not worry about. And likewise, we often have a far clipping plane because for every object we have to draw, we have to do some maths to it. So we have some points and then we have to multiply it by a transform and we have to do some other bits and pieces to figure out exactly how a 3D object gets drawn as two-dimensional pixels on a screen. So, but obviously the further away an object is from me, the smaller it's going to appear. So you guys are, you know, fairly close to me, you're quite large. But if we looked out the window and saw someone, they'd appear much smaller to me. And if they're 100 kilometers away, chances are they're going to be so, if I was able to see them, they'd be so small it would be insignificant. So we often have a far clipping plane to basically say, well, actually, once an object gets past this distance, it's kind of insignificant anymore, so let's not worry about it. And by having these, the view frustum and the near and far clipping planes, we can avoid a lot of issues that we have with things getting in front of the camera and stuff, but it also allows us to optimize to say, well, actually I'm not really, if I'm playing a game and my character can only see a kilometer in the distance, that's actually probably enough. Like, nothing's going to happen within a kilometer or outside of a kilometer that's going to have any impact or effect on the game, so let's just forget about it. And that means I can immediately, you know, if I've got a game like Grand Theft Auto with a really dense world, like a massive city, I can just sort of say, well, only the things that are in the viewpoint of the camera, viewpoint of the character, do I have to draw. Everything else I can just forget about. And that's a pretty quick operation to figure out whether something's in the view volume or not. Okay, so positioning the camera. So there's multiple ways of doing this. So obviously in Unity, if we have our camera, so we have our camera here. What's going on? So there's my camera. So I can shift its position around. I can orient it and rotate it to look at various things. But there are other ways which we can orient a camera. So there is a nice example which shows one of these in processing, basics camera MOVI, which shows how one way of rendering a camera. So okay, let's have a little look at this example and talk about what's going on here. So we have this box with some lines drawn out of it, and you can see as I move the camera up and down, it appears like the box is kind of moving closer to us and rotating towards us. But if we look at the actual example here, we'll see that the box, there's actually no transform or translate functions in here at all. The box is actually being drawn at the origin, and then we have some lines which are sticking out of it. The only thing which is moving is we have this camera function here, and the second argument is the mouse Y position, and that's literally the only variable we have in the entire example. So what's actually happening here is the box is staying at the same position, and the camera is actually just moving up and down as we move the mouse up and down. So we're not actually moving any of the geometry now, we're just moving the camera that is looking at the geometry. So let's have a little look at this camera function. So the camera function takes 9 arguments. So the first 3 are what's known as the eye position, and that is the position of the camera. So is it here, is it there, is it there, is it wherever? The next three arguments is what's known as the center position, or sometimes the look position. And that's another way of positioning a camera that Unity actually also supports. So instead of positioning my camera and then moving it to look at something, what I can actually do is I can position it and I can say, look at this point, rather than rotate around this amount and this amount. I can just say, you know, point the camera at that box of tissues. And the good thing about that is if I move my camera, as long as I just say, keep pointing at that direction, the camera will actually rotate itself So it is always facing that object. So that makes, if you want a camera which follows an object really easy, all you do is just say, point the camera at this object, and then you can move the camera around, or the object can move, and the camera will always be looking at the right place. The last three values are what's known as the up value, and effectively that's usually just either 0, 1, 0, which is the up vector, so the camera is pointing up that way. If we think of this as being X, Y, and Z. So if we say it's up, I'm holding the camera that way. Or I could say 1, 0, 0, which is 1 in the X dimension, which means that I am holding the camera that way. So really all the up value tells us is my camera pointing that way, or is it pointing that way? You can obviously set this in other ways to, position the camera in weird shapes. But anything other than sort of 1, 0, 0 or 0, 1, 0 will give you quite weird, unpredictable results, because you've told your camera, look at that tissue box, and then you've sort of told it, actually also you should be facing this direction here. Whereas if I say, look at the tissue box and up should be that way, or look at the tissue box and up should be that way, that's something which can be dealt with quite, well, is more sensible rather than other ways of looking at it.
The one is 1 meter now, the distance from the...
For the up, or no, so this is basically a normalized, we haven't really talked about this, but a normalized value. So these three numbers should add to 1. They don't have to, because it will do it itself, but basically a 1 in Y just means put the Y direction pointing up.
I think just thinking about the real world, so that 1 at a unit will be measured by meters, or so if you are using a VR headset and you just set the camera in the Y position.
Yeah, so I guess for what you're talking about is probably more relevant for the first two, so the I and the center X, and they will depend on your coordinate system. So if you've set up everything in your virtual reality environment to be in the scale of meters, then these will be in the scale of meters as well. But really, it's all arbitrary. So if I set up everything to be in centimeter scale, but as long as everything is the same scale, the effect that we will get will be that it is in the scale that we want it in. So these numbers don't actually have a direct mapping into the real world. If I told you that this is 10 centimeters long, that's kind of the same as me saying, well, actually it's 4 inches, 3 inches, whatever, long, is the same scale meaning different things. Likewise, if we all magically got scaled up 100 times like Ant-Man, and this phone remained the same size, you'd still look at it and it would still appear the same size to you. So as long as you're using the same scaling mechanism for everything, it actually doesn't matter what you choose. The important thing is just to choose something and stick with that, if that makes sense. So if you're saying, okay, this box should be, I want it to appear like it's a meter by meter by meter, and so I set its X size to 1, its Z size to 1, and its Y size to 1. You've effectively then said, okay, 1 is a meter. So if I want the camera to be 1.5 meters off the ground, I need to set the Y value to 1.5. And that way, when I see the cube, I will be looking at it as if I'm a 1.50 m tall person.
Yesterday I was trying to set my VR headset, and I was taking just one video, and this guy was setting up the position of the camera to the 0 level, so actually X 0 level. I don't know if that's related to the position. So if I'm standing with a VR headset, setting up the camera like 1 meter above, it was just sending me to to the sky.
Yeah, so
I don't know what was the relation to.
I mean, I'm sure he had a reason for doing that. Like if I say my eye height is at 0, that's fine. It just means that chair is now negative 1 meter 60, 1 meter 80 centimeters. So it depends, I could say that this ground is 0, and so my eye height would be 1.80 m something. Or I could say my eye height is 0, which means the ground is at negative 1.80 m. Like, it's all relative. You just have to pick one and choose it. So on that example, for whatever reason, he decided the eye height should be 0, in which case, any object which is below the eye height will be negative. Any object which is above the eye height will be positive. Why they chose to do it that way, I don't know.
Yeah, I thought that there was like a general measurement to say everyone is just 1 meter.
And so, yeah, I mean,
centimeters or something like that.
like, if depending on what sort of, so things like the HTC Vive and stuff like that are able to measure position in the real world, but again, it's all relative. So they may say, well, by default, because we don't know how big the room is going to be, let's put the person's eye height at this height. Because, when you put so the Vive has these control tower things, and I don't know when you calibrate it, you say how high they are, you just put them up and then you do a calibration. So they don't actually know where the floor is. So they might just say, well, let's put the person's eye height at 0 and leave it up to the game developer to say, okay, well, I want this room to appear like it's 2 meters high or whatever, because it doesn't know where the floor is, so it can't make a real world. That may be the reason, in which case it's, from a graphics perspective, it's it's all relevant. So if you want to say this is 0 or you want to say that's 0, it doesn't matter as long as it's consistent. Yep. Yeah, so I guess my answer to that one is I don't know why they said that was 0, but as long as it's consistent across everything, it'll be fine. Cool. So yeah, we have our camera, which, actually that's right, I'll open that up because I was going to talk through it. Just close a couple of these windows. So we have our camera position. In this case, we're saying that the eye is at 30 units. Let's just fire this up again so we can have a look. The eye is at 30 units, so we can see that the camera is actually 30 units to the right. If we assume that the cube is in the center of this TV, it's 30 centimeters to the right of that. It's at mouse Y, and it's 220 units in front of it. And it is looking at the position 0, 0, 0. So it's looking at the origin, which is good because that's actually where our box is. We haven't moved our box, so it's at the origin. So we've set our camera slightly to the right at the mouse Y position and 220 units out. We've set the look at position to 0, 0, 0, so the center of the cube, and we've said the up direction should be in the Y direction. So as I move my mouse down, starting at 0 and gradually moving down, the camera gradually moves down from looking at it from below. So effectively, if I've got this object here, my camera starts looking at that, and as it moves down, it's just going like that. It looks like it's kind of curving, but it's actually moving in a straight line. It's just because the camera is rotating to constantly look at the box, or the pen in this case, as it goes down. So when we get to Unity coding, there is actually a function in Unity called lookat that takes exactly it takes these two parts of the coordinates. You set your camera position, and then you call camera.lookat, and you give it the position it should look at and the up vector. So just to show you actually for the up vector, if I change this from Y being 1 to X being 1, that's the equivalent of changing it from portrait mode to landscape mode. And now when I move, it looks a bit weird, but if I pick up my laptop and hold it that way and move down, oh, actually, sorry, it should be that way, and move down. No, I was right the first time, it should be up this way. Like that, you can see that effectively we've got the same experience, but everything's been rotated 90 degrees. So that's the effect of changing that up position, is just changing between whether it should be rendered in portrait or landscape. But because it's being rendered out to this window, I'd need to rotate everything for it to end up being in the correct view. So usually the up position you can just set as 0, 1, 0, unless you're doing something weird. Okay, so that is setting up so I mentioned we have a few things. We have the camera position, the view volume, and clipping planes. So that's positioning the camera. The other thing we have is view volumes. So the view transforms the world coordinates, so these positions within the 3D environment, into the camera frame. So it's basically going to translate them from a 3D world onto a 2D plane, or the 2D frame rather. So then we have to have another projection which will take those 3D points from the view of the camera and flatten them out into 2D. And there's two main ways which we can do this projection. So the two main ways we have of rendering 3D graphics to a 2D plane is perspective and orthographic. So if I show you that box there, that looks like a fairly normal sort of box, right? So, looking at that, it shouldn't be too surprising. This is what's known as perspective. There is another way of rendering things which is known as orthographic, which looks like that. Now, if I showed you that first, you'd probably say, okay, yeah, that looks fine. That looks like a box. But if I show you this one first, if I show you this one first, and then we look at that one, it looks kind of weird because that's actually not how we perceive things in the real world. So what the idea behind perspective and orthographic is perspective uses this concept that as objects are further away from us, they appear smaller in our optical field. So if we have a cube, which looks like that, as the cube gets further away from me, the back of it should appear smaller than the front of it. Likewise, as the people who are at the back of the room appear smaller to me than the people who are at the front of the room, because as objects move away, they appear smaller. And the idea behind behind perspective, is we usually have one or more perspective points, and we just draw lines out to them. And then if I do the back of the cube like that, we can see now that if I took out a ruler and measured it, that there is considerably smaller than that length there. And that, I'm not much of an artist, but that kind of looks like a cube should. Likewise, if we look at that, this side here, which is much closer to us, is much longer than the side at the back, and that side is much longer than the side at the back. So we have this perspective thing. I'm not sure how many point perspective this is. I suspect there's at least two points of perspective there. So we can do, this is 1 point perspective. We can have 2 point perspective as well, where we render other lines to that point and so on. I'm not going to go into it because this isn't a graphics drawing class. But the idea behind perspective projection is that everything gets smaller as we go away from us, and parallel points or lines which are parallel will eventually converge at infinity. So the most common, probably the best illustration of that is something like this. So if I show you this, that seems pretty normal to us. Like that's looking down a set of railway tracks. But we know railway tracks have to be parallel because otherwise the trains would fall off them because the train's wheels are at a set distance. However, from our perspective, it appears that these railway tracks are actually getting closer together as they get further away from us, and at some point at infinity, those railway tracks will touch. And that's an effect of the shape of the lenses on our eyes, the way they bend light and so on and so forth, gives us that experience. So that's perspective projection. So the other one is orthographic, which looks like that. And what's key about orthographic is that it maintains parallelism, it maintains length and everything. So if we look at this, this example here, we know that this should be a cube, but those two lines definitely aren't parallel. Those two actually aren't too bad, but those lines there aren't parallel. So parallelism is lost. We've already looked at length is lost, even though that should be a cube. The sides appear to be different lengths. What orthographic projection does is it maintains all these things. So if we measure the size of these lines, they will all roughly be, well, they all should be exactly actually, or at least parallel lines should be exactly the same length. Likewise, all of these parallel lines should be the same length. And parallelism is maintained as well. So those two lines are parallel, so those squares should be parallel. And those are parallel, and a parallel, and likewise parallel and parallel. So the idea behind orthographic projection is it's a rendering technique which is more commonly used in engineering drawings and stuff like that. When we want to give an idea of the 3D structure and nature of something, but we actually want to be able to measure stuff off it and confirm suspicions. So I could theoretically, because I know that, well, I can measure this, that line is the same length as that line, is the same length as that line. If I actually got out a ruler and measured them, I know for sure that this is a cube, because this dimension, and that dimension are all the same length. But in this one, it's actually really hard for me to tell. It looks like it's probably a cube, but I don't know, it could be longer than, like that depth could actually be a bit longer than that height, or the height could be longer than the width. It's really hard for us to tell, but it does look more realistic. So those are really the only two projections that you're ever likely to come across. And realistically, probably the only one you're ever likely to work with is perspective, unless you're doing some sort of engineering drawing. So these are the two projections. So the idea behind orthographic projection is if we have a camera here looking at it, the projection or the frustum that it sits in is a box. And the idea behind, or the reasoning behind that is that objects at the front of the box, if you think about how much space, because this box will map onto the size of the camera, an object at the front of the box will take up the same amount of space on the camera thing as an object at the back of the box. So if we took this thing and flattened it down, that would be the same size as that, regardless of how far away it was. Also, because all of these edges of this view volume are parallel, the view volume itself will be, all the lines in the view volume which are parallel will remain parallel. So to create an orthographic projection, we can just say in processing ortho left, right, so give the left coordinate, the right coordinate, the bottom coordinate, the top coordinate, the near plane coordinate, and the far plane coordinate. So we give it six measurements, which are the 6 measurements of the sides of the projection. So in Unity, we can actually do the same thing. So let's fire up a new scene. And let me throw my orca in here, and let me point a camera at it. It's looking the wrong way. Okay, so we have a camera here which is looking at our orca. And that looks fairly normal. Might move it a little bit closer. And actually, let's put another orca behind that. What's it doing? Let's put another orca off to the side and behind it. Oh, I can't see it. Where's my camera? Okay, so we have two orca. They're at the same y dimension. One is just slightly behind and in front of the other one. And that all looks perfectly normal. So if I click on my main camera, we can see it has this camera component attached to the game object, which has got a bunch of things that we've talked about in a little bit of depth. So we've talked about the clear flags, which is basically what the background looks like. So at the moment it looks like a skybox, which gives it this blue to the light blue and then the grey bottom. But I could change that to a solid colour, and I can change the colour to anything I want. But let's leave it as a skybox at the moment so it looks nice. I haven't talked about the colouring mask, we'll get back to that later. But then we have this projection. So as I mentioned, we have two different types of projection, orthographic and perspective. So by default, Unity will set everything up as the perspective projection, which if you remember means that parallel lines don't necessarily look parallel, objects appear smaller as they get farther away, and so on and so forth. So what I can do is I can change it to orthographic, and now we'll see that these two whales appear to be the same size. Which is true, they are the same size, but one of them is actually quite a lot further away from the camera than the other one. So it's this weird sort of thing that these two now seem a lot closer than they are to us because they're the same size. They're either a lot closer or if one's further away, it's a lot larger. Likewise, if I threw a cube in the mix, see if I can get that in a position where we can actually see it. Sort of between the two of them. All right, there's my cube there. Oh, moving it to the camera doesn't really make any difference. But if I rotate this cube round, we'll see that no matter, make the game view a bit bigger, no matter which way I rotate it round, the cube appears, all four sides are the same size, and all lines which should be parallel are parallel, as we would expect. If I go back to my camera, I can see here my view frustum, so it's very, very long, so we can change so we have the clipping planes down here, the near and the far, so I can bring the far one in so it's not quite so bad. So there we go, we can see our frustum, and likewise we can see, as we saw in this example here, it is in a rectangular shape. And the way Unity works is it actually just gives you one value you can change, which is the size, because the width and the height need to match the width and the height of my game screen. Otherwise, I'll end up with black lines around the side, as I said. So you'll notice if I resize this, it's a little bit hard to see, but as I resize that to be longer, the width and the height might need to click and go back. Yeah, so you can see here that is almost square now, but if I drag that out to be quite long and then go back and forward, you can see now that it's much more rectangular. So that shape there will be the same shape as our game window, and then the length is defined as the width and height. And the only variable I can change to change the other side of it is just this one size, which will change the size of that thing, but it keeps the ratio the same. So we can see, because of the weird way that the orthographic projection works, is that effectively changing that size is kind of like zooming in. So if I add size 1, it looks like that cube and orca are really close, but as I make that number bigger, they actually get smaller and smaller, not because the camera's moving or the objects are moving, but because there's actually a lot more. All these pixels have to be mapped to the screen. So as we make the size of that frustum bigger, we're basically saying, well, each pixel, if this is at size 1, let's say, each pixel in that cube maps to a pixel on that screen. So let's say this is of length 1, and this is of length 1. That's a 1-to-1 mapping. So a point in this will map exactly to a point in that. If I make this a size of 10, so we now have 10 across here, but this is still at 1. This means that each pixel effectively across here maps to 1/10 of a pixel. So everything appears a lot smaller, but in reality it's just because we're rendering a lot more area into the same size space. So that is the orthographic projection. We also have the perspective projection, which I can click at, and you'll notice now, whoops, instead of being a cube, it's effectively a pyramid which comes out of that. So if we have a look at this on the game, actually let's just put them side by side again. Have a look at the game. So as we would expect, objects which are further away, so this orca here now appear smaller than objects which are closer, so that orca there. If I rotate my cube, it still looks pretty parallel, but if we actually measured it, certainly we've lost some of that, the length being the same. So if we have a look at orthographic, that length there and that length there, if we measured them, would be the same. If I put that back to perspective, we can now see that that length there looks much shorter than that length there. And if we measured out those two lines there probably aren't parallel. They probably do at some point off in the distance. They will meet up. So with our perspective, again, we have the same thing. So in Unity, the ratio of this perspective will depend on the ratio of the game windows. So at the moment, the shape is kind of rectangular and it appears kind of rectangular. If I make that square and we go back, you'll now see that it's square. So Unity's already handling that for us. Oops. And again, the only thing we can actually alter is the field of view. So that will change how basically narrow pointed or wide pointed that frustum is. But we actually get the same result with doing that as we did with changing the orthographic view. So as we are really close, it will appear super zoomed in. And then as we increase the field of view, it actually appears like we're zooming out. But again, it's because we're rendering a much larger area to the same space. And eventually, if we go too wide, we'll start seeing some weird effects happen, like the sun, which should be a circle, is now like sort of stretched out. So it's kind of like it's effectively a fisheye effect. Like if you put a fisheye lens on a camera, everything gets really warped out, but it doesn't render it perfectly because this is a pinhole camera rather than a lens. But it does mean that objects do start to get really stretched out. So that sun now appears to be very stretched, where in reality it should be a circle. Okay, so that's the orthographic projection. As we've just seen, the perspective projection looks like this. So it's more of a pyramid. In Unity, again, I set my clipping plane was very close to the camera, but I can actually change that near clipping plane to something a bit more, so we can see that it is actually it does actually have a flat top. And just to show you what I was talking about before, so that cube is quite close to the camera. What I could do if I didn't want to see that cube anymore is I can actually just keep moving that clipping plane until the cube is on the other side of it. And you'll notice that there it's inside the clipping plane and we can see it. There it's outside the clipping plane and it's just disappeared. So it's not that, it's being rendered as see-through or transparent or whatever. It's literally just not being rendered at all. So this is the sort of thing, you can imagine if we had our Tomb Raider character here, we might want to set the camera so that the near clipping plane is right behind her, so that we're never going to run into this case where we can't see her because she's standing in front of a wall. So yeah, we can do that. And you'll notice as well that we do end up with certain cases, even with the viewing camera here. If I try and do it this way. So this is one thing which I do find somewhat frustrating about the scene view in Unity, is that the clipping plane is actually determined based on the size of the object that you're currently, or that you last double clicked on. So if I make this cube massive and click on it, and then try and zoom in on one of these whales. Okay, I can't even get it to do it now. But sometimes you get you'll end up in the thing where for whatever reason the clipping plane of the scene camera is kind of wrong, and I'll get this close and it'll start clipping through the actual, the whale, in which case the easiest thing to do is usually click on the object that you're trying to zoom in on. Unfortunately, I can't get that to happen right now, so don't worry about it. Okay, so one thing which is kind of useful to do. So I said we have orthographic projection and perspective projection. Orthographic projection is more like engineering, so it's all more measurable and stuff, and doesn't often have a lot of uses. But what if I wanted to position two objects really accurately in Unity? So what I can do is I can move my camera around. So say I want to balance one orca on top of the other orca with their fins touching. So let's take one of these guys and rotate it so it's upside down, and then I'm going to try and move them so that the two orcas are touching and the fins are on top of each other. So what I can do is I can gradually sort of manipulate this camera around at a time, like piece by piece at a time, and go back and forth until they're sort of lined up. And that will eventually get me there, although it's really hard because it's three-dimensional space and I'm only looking at a two-dimensional slice of it at once. And so we can see those aren't quite lined up. In particular as well, if we're trying to line up specifically, like if I look at that, that looks pretty lined up until I get what in that view, but then if I go to another view, actually it's not so lined up there. So what Unity actually allows you to do is change the camera that we see things in the scene from perspective to orthographic, which often I find makes it a lot easier to line up. So let's reset that whale's position. And now I'm going to try and do it in orthographic view instead. So orthographic view, everything's in perspective by default. And you can see just under here, so this is basically the some controls control the camera view. So I can move it around, we can see that it moves. But if I want to align everything with the Z-axis, I can click on Z and the camera will move me to the Z-axis or the X-axis, the Y-axis or whatever. So I can very quickly move the camera around 90 degrees at a time. But underneath that, you'll see that it has this little thing with like a triangle and then it says left, and the left will change depending on my view, or it'll just say perspective. But if I click on that triangle thing, you'll notice it changes into 3 parallel lines, and that's changed it from perspective view into isometric or orthographic view, which we can see now it says isometric and orthographic are basically the same thing. So what I can do now is I can actually go into that, and now because we've lost this sense of depth and everything, it actually makes it a lot easier to align things. So I can align it in that view and I know that it's going to be aligned, and I can align it in that view and know that it's going to be aligned, and then I can align it in that view. And if that is aligned in isometric or orthographic view correctly, I know that now if I go back to perspective by clicking on it again, that will be perfectly aligned, because we've effectively aligned it in a view that gives us accurate dimensions rather than trying to do it in something that looks realistic. So that's something I found out embarrassingly late in my usage of Unity, and it has been so incredibly helpful just being able to click on that anytime you need to align objects together and align them in a view that gives you like a measurable outcome. And then you can go back to perspective and lo and behold, everything is perfectly aligned and measured. Okay, so that was a bit of a aside, but looking at perspective projections, it looks like a pyramid. We have our near clipping plane and our far clipping plane, and then we have our field of view, which basically defines the angle that the camera can see. So in this one, the field of view, in Unity, the field of view is related to, let's bring that near plane back, is related to the field of view of Y. So what it's actually doing is it's actually opening up the field of view that way. And because the frustum is related to the size of the game window, it will actually affect both the width and the height at the same time. But what it's actually doing is it's effectively changing how wide the camera can see in that axis there. And then we have the aspect ratio of width to height. So if we were setting up our perspective in processing, we would say perspective, the field of view in Y, the aspect ratio, which is the width and the height, which Unity automatically does for us because it knows the width and the height of the game window, and then the near and the far plane, which we can set in there. So despite the fact that these instructions I originally wrote for processing, and we used to do all these demos in processing first, it's exactly the same thing in Unity. Unity just does some of the work for you. So with the orthographic projection, you only define the size, and it will use that to calculate the left, right, bottom, and top. In Unity, you only need to specify the field of view Y, and it will automatically calculate the aspect ratio for you. So just in summary, there's only really 2 types you're ever likely to come up with. I'm sure there's probably more other theoretical projection types. I'm not familiar with any, and certainly I've never seen any in anything that I've come across. But effectively, you have orthographic, which is really good for doing measurements, aligning stuff accurately, where you give it the width, the height, the near and the far dimensions. And then we have perspective, which is more related to the way we perceive things in the real world. So, things will, parallel lines will converge, objects which are further away will appear smaller. And that has basically set up knowing the field of view, or usually the vertical field of view, so the field of view of y, the aspect between width and height, and then the near and far planes. And finally, once we've set up our camera to being a certain type, we can fix our camera view, so we can set its position. In processing, we give it the X, Y, and Z position, the center of view, so what it's looking at, X, Y, and Z, and its up coordinates. In Unity, we can just move our camera around and point at stuff. When we get to the Unity scripting side, I will talk about how we can use the camera.lookat function, which is effectively the same thing as that. Cool. Any questions about camera stuff? No, hopefully it's so good. Again, play with this stuff. You'll have to play with it a little bit for your assignment anyway, so that's the best way to learn. It's the great thing about Unity is that the fact that you have little dialog boxes where you can just change numbers, or sliders where you can drag, makes it way easier to play with this stuff than using processing or something where you have to compile, like change the code and compile it and then try and understand what's happened. Some of the processing examples are quite good, but still they're not quite as easy as Unity is with its UI elements to change stuff. Okay, so let's just talk about lighting. We'll see if we can get through that today, and then that will be a nice place to leave it. Okay, so lighting is, we're getting into stuff now which is not necessary to do 3D graphics, but it makes the difference between a good 3D experience and a bad 3D experience. So lighting is one of these things that I would argue is more of an art form than a science. So the stuff which goes on behind it is science and engineering, but making it look good, making it look nice, that's really an art form. So my company, Julian and I are engineers effectively, we're software developers, and Shun and Takeo works over in Japan, are artists. And we actually get Shun and Takeo to set up all the lighting in the environments because they're artists and they make things look really nice, whereas Julian and I can make things look okay, but it's never quite right. So this is stuff that I can't teach you to be good at because it requires a certain amount of artistic skill. I can teach you what the various parts are, but really, again, it's something that you need to play with and get a feeling for in order for it to look good. But we'll talk about the science and engineering about it, and then I will talk about some of the things that seem to work based on what I've been taught from Shun. Okay, so we are drawing a shape on the screen. We know that a shape is made up of primitives like triangles. We position it in space using transforms. We can translate, we can rotate, we can scale. We know we have a camera that looks at it. We have to position the camera somewhere in the environment, tell it what to look at. And then we have a projection which will flatten the 3D environment out to 2D. So we can have a perspective projection which will flatten it out in one way, or an orthographic projection which will flatten it out in a different way. So that will tell us how to get the vertices of those objects onto the screen. But then to actually draw the pixels, we need to know a little bit about the object itself if we want it to really look good. So when we're drawing an object, we're drawing, I shouldn't have rubbed it out, but we're drawing this triangle here to the screen. Effectively, all we know about that triangle is that there's a vertex there, a vertex there, and a vertex there. And those three vertices are connected by a triangle. We know it's transformed some way, we know it's projected to the screen some way, but ultimately all that gives us is here is this point, here is this point, here is this point, and where they appear on the screen. So we're not actually rendering a triangle at this point in time, we're just saying, well, the 3 points of this triangle, if here's my processing window or my Unity game window, here's where those 3 points actually will appear. So then I've got to draw the rest of the triangle which connects them. So what that comes down to is basically properties around the material, or the object itself rather. So in Unity that's done as part of the material, and we'll talk about the materials more when we get back to Unity, but there's some other things as well. So the geometry is the most obvious one. So if I have, I'll hold it this way so I'm not highlighting one. If I hold this on the screen, the way it looks to you is going to be different depending on if I hold it directly at you, as if I hold it diagonally. A better example actually probably is something glass like my phone. So if I hold it directly at you guys, it looks black. If I point it so that it's reflecting the light in your eyes, it appears quite shiny. So the geometry will affect how it looks. So that's the surface orientation, but it's also the view position. If I look at this screen like this, it appears black because it's not reflecting the lights. But if I move down like that, it's reflecting the lights, it appears a lot lighter. Likewise, it depends on the light characteristics. So in this room, you know, we've got windows and stuff, but you can imagine if I painted all the windows black in this room, so it's completely black, the only sources of light were in this room, we got rid of these lights and put a red light bulb in the center of the room, everything would look red. Even though I'm wearing a yellow t-shirt, it would appear red. Even though you guys are dressed in blues and reds and stuff, they would appear red or red plus some combination of another color. So the light characteristics make a big difference on how things appear. So the color of the light, the position of the light, if I have a light and I move it much closer to you, you're going to appear much more light or much more lit as if I put it at the far away from you. And depending on what sort of light we're talking about, the position can matter, but also the direction. So if it was a light bulb, like an incandescent light bulb, it doesn't really matter which direction I point it because the light goes out in all directions. But if I have a torch and I shine it round, it's going to appear very differently. Then we have properties of the material that the object is made of. So we have things like coefficient of reflection. So this has quite a high coefficient of reflection. It reflects really well. It's almost like a mirror. If I like directly hold it in such a way that it reflects the light, it's basically almost like a mirror. Whereas a piece of paper, not so much. I mean, I can sort of position it in such a way that it's like reflects more light. So that's, you know, doesn't look quite as light there as it does there because it's reflecting a bit better, but it's not like a glass surface. It's more of a matte reflection. And then there are some things which are more related to our graphics rendering code. So we have the illumination model. How do we take all these values and use that to compute what color a pixel should be? And the shading model. How do we take all these things and calculate things like shadows and all that sort of stuff? So here is a very simple illumination model. Imagine we have this purple teapot, we have a cyan-colored light, and our illumination model, we basically take the color of the light and we multiply that by the color of the material. So I put everything in normalized values, so 0 to 1 rather than 0 to 255 because it makes it a bit easier. But if we look at this and we multiply each of these channels out, so we have the red channel in cyan is 0, the red channel in magenta is 1, so 0 times 1 will give us a value of 0. The green channel in cyan is 1, the green channel in magenta is 0, so 1 times 0 is 0. The blue channel in cyan is 1, the blue channel in magenta is 1, so 1 times 1 is 1. And then again, or the alpha channel rather, is 1, 1, 1. So alpha is usually depending on its transparency, how transparent it is. So in this very simple illumination model, if we have a purple teapot and a cyan-colored light, the teapot will appear blue. Obviously, this is actually never the case in pretty much any illumination model because that is incredibly unrealistic, but it's just a simple example to sort of see what sort of computations are happening. So we can take that a step further. Let's say instead of just having one aspect of this objects having lighting, let's give it a material and give the light, or give both the material of the object and the light some different properties. So we can have what's known as the ambient lighting. So that's, you know, if we turned all other lights off and got rid of all other light sources, that would be light that just kind of exists in the environment. So, so if we covered up these windows, let's say we covered up all the windows in the building and turned off all the lights, the room wouldn't be pitch black because a little bit of light is going to seep through everywhere, and that's effectively what we're talking about when we talk about ambient lighting. So that is the light color that just sort of exists, really. So in this case, the ambient lighting is going to be the lighting that that is shown on the teapot in areas that light is not directly shining on it effectively. Then we have the diffuse lighting. So diffuse lighting is lighting, or areas where the light is lighting the object, but it's not reflecting off it kind of directly back into our eyes. So if this light source was a torch and I shined it on this teapot, you would imagine that there would be a part of the teapot that would be really bright because that's directly where the light's pointing on, and then the rest of the teapot would sort of fade out through some diffuse colours into eventual ambient colours. So the diffuse is that fading out colour, and then specular is effectively that colour where the light is kind of bouncing directly off the object and back into our eyes. So a good example of diffuse for this, or the specular for this, the diffuse colour is sort of the colour when I'm holding it, you guys looking at it like that. The specular colour is when I hold it at such an angle, the light is effectively bouncing directly from the light source off the object into my eyes. So in the real world, there are certain limitations and properties to these things, but in computer graphics, because it's all mathematical, we can do things which don't really make sense. So in this case, we've said that this is a purple teapot. It has the material is purple and ambient, it's purple and diffuse, and it's purple and specular. Being able to change these things arbitrarily on a material in the real world isn't really possible. There are certain things, so you might have seen those cars with two-tone paint so that you look at them at one angle and they look blue, and you look at them at the other angle, they look green. They sort of are the closest we can really get to being able to sort of affect these things directly. But these things in real world objects probably won't be identical, but they will be similar. But because this is mathematical, we can set these to whatever we want, so we can create effects which aren't possible in the real world. Likewise with the light, we can do things. So we can say, okay, well, this light produces an ambient light source of a grey colour. It produces a blue diffuse colour, so anything that isn't directly lit by the light will be a bluish or cyan tinge, and anything that the light is directly shining on will be white. And what we end up using the same colour model that we had before, the colour we see is the light colour multiplied by the material colour. If we shine our light, which emits a grey ambient colour, a blue diffuse colour, and a white specular colour, when we multiply them out, we get these colours here. So our result is that areas which aren't directly lit by the light appear black, areas that are indirectly lit appear blue, and areas that are brightly lit appear purple, which, you look at this and it just looks kind of wrong and kind of weird, but this is something that is possible with 3D graphics. I think we have one more slide in this, and then we'll stop there, but maybe we can have a look at it in Unity later. And I'll just actually open this up. So I'm starting to lose my voice, so I just want to wrap up probably after this slide. So here's an example showing this sort of stuff and the improbabilities as well of lighting in 3D engines. So here we have a ball, at least as far as we can tell it's a ball, and there are 3 light sources. There is a light source from underneath, and there are 2 light sources which are shining directly on the object. Now the light source from underneath appears to be, well, it's when we see it from underneath it's bluish. This one dot that I can control with my mouse is kind of a bluish colour, and there is a yellowish colour on the ball. Does anyone want to hazard a guess at what colour this ball is? So we've got a couple of yellows. So let me just check. I think there's a way I can turn all the lighting off. That's great. So again, it's we're capable of doing stuff that either isn't possible or doesn't really make sense in the real world. So it's actually a grey ball, and we have 3 lights on it. A blue light, so blue and grey, it's going to be blue. And then another blue light, so blue and grey is going to be blue. And then a yellow light, so yellow and grey. I mean, anything grey is just going to kind of make it a darker shade of that. So I mean, yellow would seem the safe bet for us, like being people who experience the real world every day and know how things light. But this isn't the real world. This is computer graphics, so we can do stuff which doesn't make sense. So in this case, we've got 3 light sources, 2 which are blue and 1 which is orange, which is shining on a grey sphere, or a white sphere is probably actually, oh no, it is grey, so fill 204, so it's a slightly grey colour. Let's leave it there for now, and when we come back on Thursday, we'll talk about what the different types of lighting are, and then we're actually not too far from finishing graphics, and we can get back into Unity, which is good because you'll be getting your assignment on Thursday. Cool. Otherwise, if anyone has any questions, feel free to fire away. Oh, yeah, I'll stop it.